Hello everyone, and welcome to our video on finding a particular solution when we have an infinitely many solutions case with our solving the system of equations. So when in the last video, which was involving these problems, and it's all erased now, but we had the case where it's infinitely many solutions, and they all kind of start the same, where we are going to use a calculator, so we'll do it the quick way. And we'll find our general solution. So like in the problem below, this first example, it's as if we already did the work to solve a problem and we got our general solution here. So they're saying here are our general solutions that are given. In this video, we're going to find the particular solutions. So there's usually some type of restriction on our solution set when we have infinitely many solutions, because, well, most of the time, say it involves an application. So like in applications, you probably can't have like negative values. So that means you can count out some of the solutions. All right, so in these, we have our general solution, and then now we've got some restriction to it to find a particular solution. So in this example, it says the general solution to a system of equations is given. If x, y, and z are non-negative integers, how many solutions are possible? Okay, so non-negative integers. So non-negative, so that means it's got to be 0 or positive. And then integers are your counting numbers. So really, so combining these two together, so it's saying you could have 0, 1, 2, 3, so forth. So no fractions, no decimals. Just 0 and positive whole numbers. So 1, 2, 3, 4, so forth. All right, and then they're asking how many solutions are possible. All right, so let's find this. So in these general solutions, remember that this is an x-coordinate, y-coordinate, and z-coordinate, except they've written it in the form where z is the parameter. And so that way, our solution is ready to go with only z expressions. And so the way that we can break these down, we can do these in kind of different ways. For instance, we could set up a table if we really want to. So here's our x, y, and z. And for instance, I could try to plug 0 in. If I plug 0 into the x value, well, then I'd actually have to solve some things. So actually, instead of starting with x, it's easier to start with z. So often we start with x, so that's what I was going to, but it actually makes things a little difficult. So in this problem, so the z is the parameter, it's usually best to plug in values to z. So I'm going to start and just see if this table works. Sometimes the table works where you don't have to do too much work. Sometimes it might lead to problems. So let's see what happens in this case. So if I plug 0 in, so I'm letting z be 0 in all of these portions. So z, z, and z. So if we start with z equals 0, notice my x would be 0 minus 6, which would be negative 6. At this point, I can quit this section because I have a negative value. Okay, so right now, z equals 0 is no good. So that's no good. Okay, so I put an x. Maybe I'll just write no good instead because x could be confusing. Okay, so and I'm not even wasting time to find y because I have a negative. Okay, so moving on, let's plug 1 in. Well, if I plug 1 into the z, 2 minus 6 would be negative 4. Again, no good. Okay, so keep moving on. 2. If I plug 2 in, well, it looks like the pattern will continue. 4 minus 6 is negative 2. Still no good. When we plug 3 in, I would have 6 minus 6 is 0. Now that's looking okay. And then now let's continue our work. Well, if I plug it into the y portion, 6 minus 3 is 3. So this is all good. These are 0 or positive whole numbers. So that means that's one of our solutions. And then let's keep going. Okay, so it looks like the table's going to work fine. Let's make it a little longer, though. So if I plug 4 in, it'd be 8 minus 6 is 2. And notice the pattern that's developing as well. So most of the time it develops a nice pattern. But when we plug 4 into our y, it would be 6 minus 4 is 2. So this is also good. They're all positive whole numbers. Our next case is for z equals 5. So if we plug 5 in, 10 minus 6 would be 4. 6 minus 5 would be 1. And this is also good. Okay, so these are all positive and whole numbers. Let's see what happens when we plug 6 in. So 6. 6 times 2 is 12, minus 6 is a 6. 6 minus 6 is 0. Okay, so now this one is also still good, but you might be seeing, oh, the pattern's looking like it's going to be a negative number in the next one, and, well, you'd be right. So sometimes you could start just working with the pattern alone to get all of these values, but might as well just finish it off. If I try to plug 7 in, we would have 8 for the x value, but we would have -1 for the y value. Okay, so these that I'm going to highlight in yellow, so these are the reasons why these solutions are no good. Okay, so this one's back to being no good. And then if we were to continue the pattern, if I were to continue it, notice it would have been -2, so it just keeps being negative for y. So the bigger z gets, y is just going to stay negative. So it looks like these are our only solutions. So we have 4 total solutions. Okay, so that might be, so we might have some type of general solution that is infinitely many. So this is an infinitely many solutions answer. But based on restrictions, and this could make sense if, you know, we can't have whole number, or we can't have decimals or negatives. So that makes it reduced to where we have, hey, only these 4 situations would work. Okay, so on number 2, we could try it with the table again. Okay, or let's try it a little different. So if we try the table, I think it could work out just fine. But we would have to kind of see some other patterns involved. Let's try this one instead with a different method, especially because we have fractions in our coordinates. So this is still our x, that's still our y, and then there's still our z. And so we're going to take this and set it to be, if you have 0 or positive, that means it needs to be greater than, so let's change this also into another way to say it, greater than or equal to 0. But still, we need to make sure that there'll be integers and no decimals at the end. But at least with this, greater than or equal to 0 has a symbol. There it is, greater than or equal to. So that means we can split each of these individually and set it up as an inequality. So there's one inequality. Here we've got another one. -3/8 z plus 25 is greater than or equal to, oh, I wrote 8 for some reason. So sorry, they're all 0, greater than or equal to 0. I think I was looking at the 8 next to it. Okay, so sorry about that. Let's change that to 0. So greater than or equal to 0. There we go. And then the last one, z. So I'm going to kind of squiggle to block that off. Z would also be greater than or equal to 0. Okay, so the z greater than or equal to 0 is already solved for. We don't have to do anything for it. But these other ones we can solve for. Well, solving inequalities, linear inequalities, is really pretty much the same thing as solving an equation. But there is one tiny little rule that we'll have to throw in one of these cases. So for this first one, we'll just subtract 1 to both sides to get 1/8 z is greater than or equal to -1. And then if we multiply by 8 on both sides, that would give us z is greater than or equal to -8. Okay, so there's one part, and I'm just going to squiggle it around for now. And then our second equation, we can subtract the 25 to the other side, and we'll get -3/8 z greater than or equal to -25. And then let's multiply by the reciprocal of the negative. So let's do -8/3. So we're multiplying everything by -8/3. Let's go ahead and put those in parentheses too to show the multiplication. And when we multiply that, so the negative cancel, the 8 and the 8 cancel, the 3 and 3 cancel, so we have z. However, this is the one little rule we have to catch. When multiplying inequalities by a negative value, we need to switch the way the inequality points. So let's add that rule to the top in case we're doing it the inequality method. Okay, so multiplying or dividing, if we were to divide, an inequality by a negative we need to switch the way the inequality is pointing. So I'm just going to say switch way inequality points. And so the way I'm thinking of it like kind of like an arrow. So the arrow was pointing to the right. Now it needs to be pointing to the left. Okay, and then when we simplify the right side, we do get positive. Remember that can put a 1 under if we need it. 25 times 8 is 200. And then divided by 3. Here's where it might be useful to quickly divide that. So 200, let me just use my calculator, my computer calculator. 200 divided by 3 is 66.67. Okay. So we've got Z. I'm going to put it to the side. Okay, so there we go. Okay, and what we're going to do is kind of make a number line. Okay, so this is, so far you might say this method seems worse, but if we were to make a table, the table would have to be pretty big. Okay, so the table works out, like in this case, it worked out real nice because there wasn't that much work to do with it. In this case, if we were to have tried a table, we would have needed a lot more paper. So this is actually trying to help it go faster. And you could try this same method that we are using now on number 1, and it will work out also kind of nice. It's a little faster than what we're doing right now because the numbers are easier. But this is good for when it gets a little bit more complicated still. Okay, so what we got, so this is like, we're going to say this is the z-axis. So this is just the z. And this first one right here, I'm going to plot -8 down, and then it's saying greater than or equal to -8. So we're going to mark that with black ink and say, hey, that means it's all the numbers to the right of -8. Okay, and let's go ahead and make our number line a little bigger. So sorry about that. Let's go ahead and make it a little bigger. Okay, and then our other one, let's go ahead and do that in, we'll do this in purple ink. So 66.67, let's put that right at the edge. So here's 66.67, and what we would have on that is, well, another way to show it, everything less than 66.67 would be, I'm just going to kind of stack them on top of each other, would be everything to the left. Right there. Okay, so we've got this number line set up, and then what we can do after that is, well, we need to make sure, so this is trying to condense the answer, so we're between -8 and positive 66.67. Well, we do have to make sure we go back to, let's highlight this, we need zeros or positives only. So we're going to make sure our values are either 0 or positive, and then they eventually give us only integers. Okay, so from -8, we would not have any type of answer until, I'm going to put a big dot, 0. Okay, so this looks like this could be one of our first answers involved. Using z equals 0 looks like it should give us an answer. Now, the next value that works, so for instance, like 1 won't work because we want to go back and think, well, if I were to use 1 for z, notice that in our 2 coordinates, let's go ahead and highlight these. Really just the fraction portion is what's important. If I plug in 1 into z, this 1/8 times 1 will keep it in as a fraction. So that won't make it a whole number. So instead, I just want to look at these values and say, well, if I have a multiple of 8, that would make z become, or that would make the whole coordinate become a non-fraction. Okay, so looking at those right there, it looks like, okay, so a little bit out of room. I'm going to squeeze it right here. Z is a multiple of 8. Okay, because, again, right here, if I plug in 8, that would cancel out the 8 in the denominator, and then from there, it looks like I could have a whole number. And the same deal with the y-coordinate. If I plug 8 in, or 16 or 24, all of those would make the 8s cancel, and then from there we would have a whole number. Okay, so 1 doesn't work. Instead, let's just count by 8s. So I'm going to just kind of convert it into 8. And let's keep counting by 8 until we get to right close to 66.67. So we can't go past 66.67. So I'm just going to keep counting by 8. So 8, 16, 24, 32, 40. And it looks like I probably don't have enough room to continue counting like this, but 48, we're almost there. 48, I am just going to put it on this line. One more, a little too tight on the room. Okay, so we'll say that that's where 66.67 was. So I'm still just counting by 8, though. So 8, 16, 24, 32, 40, 48. The next one is 56. And then the next one would have been 64. And then after that is bigger than 66.67. So it would be 72. And so now we no longer need it. So all of these ones in blue, starting at 0. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 values that are in between the negative 8 and the positive 66.67 that can go into the 2 coordinates that have fractions in it to turn them into whole numbers. Okay, so that's how this one gets broken down, or this is at least one way to do it. So our answer for this is we have 9 solutions. Okay, so that's using the number line method. Okay, if you didn't like the number line method, I mean, the table is still fine. The main thing in using the table would be that we'd have to catch this regardless of whichever method we use. Z would have to be a multiple of 8. So you could try to set it up and use Z as 0, 8, 16, so forth. And then actually the table's not the worst thing in the world. Okay, so and then from there you could start plugging into the x to the values to get your x's and y's until you have something that is not a positive whole number. Okay, so you could kind of treat it like the table still. All right, well, anyway, let's do one other type of problem. So these are just if we already have the general solution. These are a little tougher, I think, to find the general or the particular solution to than these actual word problems. So the word problem just needs to get converted. And then from there, I think it does become nicer. So let's see if you agree. So on this example, we've got Surfer Joe builds surfboards. It takes him 6 hours, 8 hours, and 8 hours to cut a shortboard, a longboard, and a fishboard, respectively. Then it takes him 3 hours, 5 hours, and 2 hours to ocean-proof them, respectively. He can spend a maximum of 112 hours per month shaping them and 64 hours per month ocean-proofing them. How many boards should he make to maximize his time? All right, so let's break this down. Okay, so it says Surfer Joe builds surfboards. Let's use blue here. It says it takes him 6 hours, or let's use black ink, sorry. 6 hours, 8 hours, and 8 hours to cut shortboard, longboard, and fishboard. And then it talks about some other time. Let's do this in purple. It says then it takes him 3 hours, 5 hours, and 2 hours to ocean-proof the longboard, the shortboard, longboard, and fishboard, respectively. He can spend a maximum of 112 hours. So that's going to be our total number of time that he can do. So right there, I'm just going to mark it to the side here. So that's total time. 112 hours per month shaping them. So total time, 112 hours for shaping. And then 64 hours for ocean proofing. There it is. Okay, so total time for ocean proofing equals 64 hours. Okay, so there's the totals. And then how many boards should he make to maximize his time? Okay, so let me underline this. I'm going to use black ink again. How many boards should he make to maximize his time? Well, it's asking how many boards. So that means those are variables. So x is the number of let's just do whatever's first, short boards. Y is going to be the number of whatever the second one is, so let's do long boards. And then Z looks like it should be the last one, number of fish boards. Okay, so those are our variables. And then now all we have to do to set up our system is to set the times that are related to whatever variable as their coefficients. So in the black ink again, the first one, it says 6, 8, and 8 for short, long, and fish. So that means 6x, and then we'll just keep adding, plus 8y plus 8z equals the total it takes for cutting. Okay, and they didn't use that same vocabulary when they gave the totals. So this is always our total at the end. They talked about shaping and ocean proofing. Well, I believe shaping would be for the cutting. So let's say this is equal to 112. Okay, and then the second line, let's keep that in purple. Let's just attach those coefficients to their respective variables. So 3x plus 5y plus 2z equals the total amount of time it takes to ocean proof. And then here's the 64 that we marked from before. Okay, so we've got it. So we got it set up. And then now we need to solve for x, y, and z. Okay, well, to solve for this, let's convert it into a matrix. So x, y, z. And then our total is our constant. And then we've got 6, 8, 8, 112, 3, 5, 2, 64. And then this is where we'll use our RREF function on our calculator. And for now, I'm just setting everything up. Okay, so we've got our RREF. I'm going to use my free resource, Desmos, desmos.com, and then the Math Tools matrix. And then let's set up that matrix. So, oops, I don't want to do that yet. Let's just say new matrix. And then we've got, all right, so 2 rows and 4 columns. And then we'll enter those. So 6, 8, 8, 112, 3, 5, 2, 64. Enter. And then now let's use the RREF function. So RREF on matrix A. And, well, there it is. So we've got 1048. And then 0, 1, -2, and also 8. Okay, and then at this point, this is where we'd want to convert them into their equations again. Let's number them 1 and 2. So for number 1, the equation becomes 1x plus 0y, so I don't need to write 0y, but then I do have 4z would equal 8. And then the second equation, 0x's, I don't need to write that, but we could write y, and then minus 2z equals 8. So there's the 2 equations. And then what we want to do is write our general solution like how these first 2 are just given. So let's get our general solution. So remember, our general is in the form x, y, z, but we want to use z as the parameter, so these will get converted into z expressions. And while they're easy to change, because with equation 1, we can instantly just subtract 4z on over. So we'd have 8 minus 4z. And so that would be our new x-coordinate. And then same deal, it's easy to solve for y. We can just add the 2z on over. So we have 8 plus 2z. And then z is still the last coordinate there. Okay, and so we have a general solution. So I just wrote general. Let's put general solution. And then let's go back and see what they wanted. They said, how many boards should he make to maximize his time? Okay, well, this is where we're going to make our table. Let's do the table method. This will be easier for this problem. Usually with a word problem like this, they don't make it where it's crazy once we're here. And so with our automatic restrictions, the number of boards, these have to be either 0 or positive whole number. So you can't have fractions, you can't have negatives. So that means I'm just going to start with, let's set up at least those 4 and see how it goes. Okay, so when we plug 0 into to the z, I'm looking at my values there that they would get plugged into as well. So when I plug 0 into the z, let's only focus on the x first. I think that might make things easier. So if we plug 0 into the z for the x coordinate, it looks like it'd be 8 minus 0, so that is 8. When we plug 1 into z for the x, it'd be 8 minus 4, which is 4. When we plug 2 into the z, we'd have 8 minus 8 is 0. And then when we plug 3 into the z, 8 minus 12 would be negative 4. The reason I only stuck with x at the moment was, well, it looks like there's an easy pattern to see if we needed to get more values. But on this, we don't. So we actually are done with that. And then now let's do all of the y. So if we plug 0 into y, we're going to have 8 plus 0 is 8. If we plug 1 in, we'd have 8 plus 2 is 10. When we plug 2 into the z here for our y coordinate, we'd have 12. And then here's again, we can start to see a pattern, 8, 10, 12. Plugging 3 in would give us 14. And if we needed more, we could keep seeing the pattern. Okay, however, we can't stop because here we've got a negative. And our pattern would tell us that the next one would also have been negative. So all of these ones from here on out are no good. Okay, so all of these are no good after z equals 3. So it looks like these are the 3 solutions that he could do. So Surfer Joe's got 3 ways he can maximize his time. And if they really wanted in words, I'm kind of running out of room. Let's put it like this. So 8, 8, 0 is one option. 4, 10, 1 is one option, and 0, 12, 2 is another option. So he could do 8 short boards. So these are the number of short boards. These are the number of long boards, and then these are the number of fish boards for the 3 different cases. So 8 short boards, 8 long boards, and 0 fish boards. Or he could do this one, 4 short boards, 10 long boards, and 1 fish board. Or he could do this one, 0 short boards, 12 long boards, and 2 fish boards. Okay, so these are the 3 solutions. So whichever one of those he wants to work on, that would maximize his time. Those are the 3 specific, particular cases for this infinitely many solutions problem, though. Okay, so that's it. So the particular cases, these are kind of the worst, right? Okay, so they take the most time. Just be patient with it. Stay with it. Take breaks when needed. Okay, but that's it for now. If you do have questions, please let me know. Otherwise, thanks for watching, and I'll see you again soon.